Hi, this is section 6.1, and we're dealing with slope fields. Slope fields are mathematical representations of possibly different slopes that occur in the world. So here's one example that I do have here, and this is magnetism. So we have some iron shavings, and then the magnet here has a force field that it projects out. And so how does it react? Well, it reacts by making these shavings all go in a certain direction. Now what I can do is I can find a particular point here, and I can find the slope of what's going on at that particular point and see what the waves of this magnetic field are doing. That's kind of the idea of the slope fields. Now where else do we have slope fields? Well, you might have currents. They show up on waves, or currents in the ocean, and also air currents over a country or over an area, or even airplane dynamics. You know, they put the cars and airplanes in wind tunnels just to see how they react. They put smoke out there, and then you can see kind of how the wind is behaving in certain areas. There's another cool one that I found too. This isn't metal shavings, but it's a liquid, they call liquid iron, that reacts to the magnets as well. So the slope field is generated by the slopes from a differential equation. So we're finding we have a derivative. The derivative tells us how a curve is behaving in a certain rounded area. And so that's what the slope field does. And in calculus, we have all these equations that represent these slope fields. But if you take the air patterns over the United States and look at those vector fields, which they call them in physics, they're not going to respond to an equation. So most of these things you can't use an equation for, but what we have in mathematics is equations to represent these, and then you get a better feel for them. So let's look at the first example here. Find the slopes given by the differential equation negative x over y at the following points. So all we do is we take 3, 2, if we're doing part A, and plug it in to my differential equation. So if I do the differential equation evaluated at 3, 2, I'm just going to get negative 3 over 2. Make sure that the x's and y's, you don't get those mixed up. That's what happens sometimes. Why don't you try B, C, and D and see what you get. Pause this. So what we're going to do is take all of these slopes that we did find, and we're going to put them on a coordinate plane. Now some things you should realize though is that slope equal to 0, you're going to draw a horizontal line like this. Slope of 1 is going to be at a 45-degree angle, like so. 1/2 would be less than that, and 2 would be greater than that. So you got to put everything in perspective as you go. I also can have negative slopes. So if I have m is equal to -1, that would be at a 45 going down. This one would be less than that. And then this one, that should be a 2. Doesn't look like a 2. And that should be like that. So when you draw these, that's the kind of perspective that you're doing. So if I look at my first one here, at the point 3, 2, I get a slope of negative 3/2. So let's go 1, 2, 3, and 1, 2. That would be a slope of negative 1.5. That's what that looks like. If I go to part B, negative 1, and then 3, this is a slope of 1/3. That looks about right. It's up to the right. This one is a slope of 2 at negative 2, negative 1. So here, that looks about like the slope of 2. No, it doesn't. That's because I made a mistake here. So that should be a negative 2. And then D, if I plug in 2, negative 2, go to 2, and then negative 2, I'm going to plot a slope of 1. Now if you notice, there's some patterns going on around here. I don't have lines here, but I am undefined at y equal to 0. So we're undefined, and then that means that we're doing division by 0. So for instance, right here, at the point 1, 0, I'm going to get dy dx is equal to, well, we're using this again, so this would be negative 1 over 0. We know that this is undefined. And so we might think, well, slope undefined, we're going to make a vertical slope line. Well, we don't do that. Remember that we want to try to keep our functions to be functions, and so we're not going to have any situations like this. And so all along here, we're going to have nothing. And so it's just going to be blank. And so when we draw what's going on for our function, we're not going to represent anything over this line right here. Nothing's going to be crossing that. Nothing's going to be dealing with that in particular. I'll show you how that works in a second. So I started filling in the rest of these dots with these blue lines. And you can go ahead and find the symmetry. This one has nice symmetry. They don't always, but sometimes you can find that. And I'm going to keep on filling in the rest and come back to this. You can try to do some of them yourself too. So there I got my symmetry, and I filled in all these little slope lines. Make the segment long enough so you can see what the slope is, but don't make it too long so they're rolling into each other. Now this just gives you what happens in and around an area. So what I'm going to do now is look at my slope field and then go to example number 3 here and see what's going on with what this is saying. So now it says start at the point 0, 1. So I like to think that the slope field itself is a bunch of currents in the water. So what I'm doing now is I'm, for instance, dropping my hat in the water at 0, 1. Where does it go? Well, we don't have direction on these. That would be a vector field, but with the slope fields, we're going to go in all directions that we can. So if I drop my hat in the water right here, at 0, 1, I'm going to be going like this. And if you notice, all of these things kind of look like semicircles as we go around. And that's what's happening. And so we don't go right through these lines, but we kind of see the shape that's going in around those areas. Now I said since we're undefined here, we're going to have a hole. So we're going to go up to that point, but we can't cross over, and then we're going to have a hole there because we are undefined for our slope field. Now we're going to go ahead and go on to the rest of this. So we just did accomplish this task. We're going to go on to the next task. And this one just does say about the average of slopes. And so when you take this region right here, you kind of, if you're going in between them, you just kind of get a feel for what the slope is in between those different little slope field marks that you do have. So if I move on now to negative 1, 1. What if I drop my hat in the water right here? What would happen? Well, I'm going to go here, and since my dy dx is undefined there, we're not going to go over that mark and not include it either. And so we're going to end up with a semicircle that's not defined at the end points of that semicircle. And then our last one, if we go through 0, negative 3. If it's 0, negative 3, I'm going to stay at the bottom all the time. So I'm going to go here, and I'm going to go through this point, which is 3, 0, since it is a circle. We don't always know that it's a circle, but that's kind of the general shape that we're going to end up with. Each one of these is what we call a solution curve to the differential equation that we do have here. And so wherever we drop our hat in the water gives us the particular solution. This should start making sense to you from what we've done before with particular solutions and finding different values of C. That's exactly what all of those different little solution curves that we just drew through different particular points are showing us. Okay? Then the last note down here, don't draw these things too far. Make sure that it is a function that we are drawing, and don't go too much over what we do need. So let's try this example 4 and see what happens. So I have dy dx. If I separate the variables, I'm going to bring the y over, is equal to negative x dx. Then I integrate both sides, and I'm going to get y squared over 2 is equal to negative x squared over 2 plus c. Now I can change this c by multiplying everything through by 2. So y squared is equal to negative x squared plus that c. Now what happens is that we want to solve for y. In instructions, a lot of times, they'll ask for the solution y equals f of x. That means solve for y. And when we do this, we're looking for a function. That's some of the discussion I just had previously. So if I do this, this is y is equal to plus or minus the square root of negative x squared plus c2. So one of the solutions would be square root negative x squared plus c2, or I could have the opposite of that, like that. So I'm going to end up with two different possible general solutions for this thing. Now we go to the particular solution. If I plug in the 0.01, what's going to happen? Well, I have the plus or minus situation here. Well, what is my y coordinate here? Well, it's a positive. Am I going to get a positive yielding from this equation or this equation? Well, I hope you understand that it's going to be this equation because it's got the positive out in front. So that's the one that I have to use. So I have the positive square root, plug in the values that I know, and solve for C2. I didn't plug that in, so that's a 0. And so if I solve this, I get C2 is equal to 1. So this is my particular solution. Let's look at this example here. I'm rolling through the point 0, negative 3. So which one am I going to be using? This one or this one? Well, the negative 3 tells me that I need to yield a negative 3 for my y coordinate, so it has to be that equation. So I have this equation here, and so I plug in the 0, negative 3, and you get this equation here. I lost a lot of these negatives, these squareds, and so make sure you put those back in if you missed those before. Should be negative x squared under the square root symbol. I missed that in a few places. Make sure you get that in. And here, I need to yield the negative 3, so I need the negative there. So that was the whole point of that problem. So the y coordinate tells you, are you on the upper half of the graph, or the negative tells me I'm on the lower half of the graph. So this would be the pictures of what you would end up with for each one of these solutions. So since I wanted a function, I only wanted half of the circle, the semicircle, either top or bottom. So I hope that kind of clarifies what I was talking about before. Example number 5. Differential equation, y prime is all in terms of y. So if I want to draw all these, notice that when I have y equal to 3, what happens? Well, my slope's always going to be 1/3 regardless of what the x is. So when I go up here to y equal to 3, I'm going to get 1/3 going all the way across. And if I go here, where y is equal to 2, I'm going to get 1/2 all the way across. And then at 1, I'm going to get a 1. This is a few too many lines for me to do a good job, sorry. But this is what it's going to look like. Then you can finish that up. So I finish up that bottom. Now if you look at what they asked me to do, graph the particular solution. So for instance, if I go start and drop my hat in the water at -2, -1, I'd be right here. Now notice I have this kind of separation point again. Probably going to run into trouble there, so I'm going to make sure that when I go this way, I'm going to have the open segment there. And then when I go this way, I'm going to end up like this. Something like that. This is flattened off too much, sorry. Drawing on this pad isn't the greatest, but I'm trying. And then 2, 2 would be the other one that I want. So 2, 2, I go to this point here, and it's a very similar type thing. Looks like I go like this. So it's going to be a sideways parabola. So maybe when I solve this thing, which it says right here, I'm going to end up with, so dy dx, bring the y over, can bring the x over, is 1 dx. So I integrate both sides, y squared divided by 2 is equal to x plus c. So I can multiply both sides by 2. 2x plus, well, now I got a different c. And so then I take the square root, so y is equal to plus or minus the square root of 2x plus c1. Now when we look at these points, what's the y coordinate here? Well, it's negative. So this one is going to be y equals, and now I'm finding the particular solution if you can read that. Y is equal to negative square root of 2x plus c. That's the one I want to select for this. So I have the -1 is equal to negative finish both of these up for you. Double check them. I hope that you're running through this and pausing and trying these. But I get y equals negative square root of 2x plus 5 because I have the negative y value. And then over here in the blue, I have y equals square root of 2x because I have the positive y. That's how it works. For example, 6 and 7 are very good because what will be done to you is that sometimes they'll give you the differential equation and sometimes they'll give you the equation that satisfies this slope field. So if you look at example number 6, they are giving you the differential equation. So that would be what's generating the slope of all these little line segments. So when I look over here, well, there's a couple ways to do this. If I did try to draw a solution, this looks kind of like a cubic. So possibly what I'm looking at is something with a squared value in it. And it is all the same top to bottom. So this going top to bottom is all the same no matter where we're at. So that means that I'm going to be exclusively in terms of x. So if I look at this, I can exclude anything in y because y would be going all across the same. And so what else do I got? I can exclude that. This one is x and y, so I can exclude that. So it's either going to be this one or this one. Well, I'm going to say it's going to be this one because my solution would be a cubic. So that means that my differential equation should be a quadratic. All right, so this is not the equation of this curve that I just drew, but it is for each one of those slopes. You can also go through and check a little point here. Negative 1, 1, and you got a positive slope. Everything comes out positive, so then we do have that there. Then example 7, they give you the solution. So I want to know what the solution would be. So it's one of these functions here. So that's what I would be drawing. So if I dropped my hat in the water on these, look at what happens. What does that look like? Well, that looks like an exponential decay equation. So I'm not going to have this, I'm not going to have this. Now if it keeps on rising, looks like it flattens out quite good. If it slowly went down, then maybe I'd be looking at ln x or negative ln x, but in this case, it looks like it really flattens off, and so it's going to be exponential decay, which would be y equals e to the negative x. This is the solution, so I graph this thing, that's what I'm looking for right now. All right? And just for reference, this is y equal to negative ln x. It would have a vertical asymptote, and then it would slowly still creep down. This one really looks like it flattens off, so I got to believe that's exponential. So on your TI Inspire, you can go and graph these things using the graph entry. So go to the graph mode, graph entry, differential equations. Unfortunately, I only know how to do this in terms of x. There's programs, applets on the computer that you can go to that will do x and y, but that's all we have for this. Then if we go beyond that, y prime will show up. So with y prime, you just type in what the differential equation is. And then you'll get something like you have down here. This is the graph of dy dx is equal to sine of x. But now if I graph this, like if I drop my hat in the water and I wanted the solution curve, notice what the solution curve is. It's not sine of x that I'm drawing there. This is y equals negative cosine of x plus some constant. This is the drawing, is the differential equation. I'm sorry, I said that wrong. Is the solution. And then this is the differential equation that we do have. Now I also can put in a point here. So if I put in 1, 0, I would go to 1, 0 and it would graph the solution curve for me at 1, 0. Here's an example where I plugged in the point 2, negative 1, which is right there, and then it gives me the solution. So play around with that, try that, it's kind of fun. The next thing we want to look at in 6.1 is Euler's method. Now Euler's method is a way to estimate a value. A lot of times we know the differential equations, but we don't necessarily know the solution curves. Or we know how the slope is at a point, but we don't know what the actual curve is. So we can estimate points using Euler's method. So this is, it's a lot of tangent line approximations, and you can do it different ways. Y of some new value b is equal to a starting point plus my change, which would be slope times x minus x. All right. Now there's different ways to do this too, and this chart that I'm going to set up is just going to do dy dx times this delta x. And I kind of like the way that he does it here. So I'll show you both methods, one with the tangent line approximation and then one with just the change. So here I'm given a differential equation, dy dx is equal to y. I have a starting point, and then they also give me a step size. What I can do is figure out what a value might be for an estimate for this curve in around that area. So let's estimate this differential equation in and around the area of 0, 1 with step size 0.1. So I'm going to start off with this point. So we always start off with our initial point and then find the slope at that point. Well, they tell me dy dx is equal to y. Well, that's just the same as this y coordinate right there. So whenever I have something here and this y coordinate, it's going to be the same thing here for this particular example. And then we want to know how much our delta y is going to change. So delta y is equal to my slope. My slope is 1, so I get that from here. And then I want to multiply it by our change in x, which would just be 0.1. What do I get? Well, I get 0.1. So that means that I'm going to dial up this 1 by 0.1 to get to my next value. So I'm going to get a 1.1. Now what is my x value? Well, I increase by 0.1. So in other words, the change in x is going to be given to you. That's what I'm going to be going up by. The change in y you have to find. Okay, so it's not this 0.1, but it is this 0.1 right here that the y changes in. What's my slope now? Well, it's going to be 1.1. The change in y then is going to be 1.1 times that delta x again. What is that value? Well, my change here is going to be 1.21. So this would be 0.2, 1.21. So that's what I'm changing by. My slope, dy dx, is the same thing as this y coordinate. So I'm going to get 1.21. So my new delta y is going to be equal to, what I got, 1.21 times 0.1. So what are my x's going up by? Well, they're going up by 0.1. That's what it's telling me. What are my y's going up? Well, in this case, it's going to go up by this number here. This number is 0.121. So if I add that to the 1.21, I'm going to get 1.331. Okay, so these are all estimated points on my curve. So when I do this, this is, let's see, 0, 1. We start at 0, 1, which is right here. Then my next point is going to be 0.1, 1.1. And then my next one is going to be 0.2, 1.21. And then my next one is going to be 0.3, 1.31. So I think I'm going kind of sloping off, tailing off a little bit, but we're really zoomed in. So that's approximately what's happening to our curve. Example 9 says, well, let's do this actually so we can see what's going on with this. So let's separate our variables for this one here. So I need 1 over y dy is equal to 1 dx. And I'm going to integrate both sides. I'm going to get ln y is equal to x plus c. And we know the routine here. This is going to be c e to the x. And so if I solve this for my particular solution, I'm at 0, 1. So when I plug that in, 1 is equal to c e to the 0. So c is equal to 1. So we just get y equals e to the x. Plug those values in, do your calculator, and see what my y values are. And I want to compare them to those. Okay, let's compare at 0.1. At 0.1, I get 1.1. Ooh, 1.105. That's very close. Then at 2, 1.21. oh, that got off a little bit. Oh no, I got that wrong. It is 1.221. That isn't very far off. And my last one is 1.331 and 1.350. Notice as the farther we get away, the further away from the curve that we do get. If your curve is very stable, you probably, if it's concave up or concave down, you'll probably get further and further away from the curve as you go on with these different values. But not a bad estimate at all. So really what we're doing is using little tangent line approximations in order to do this. And from this equation here, we are finding this right here. This value will always be the same. This is your delta x. Your dy dx is going to change each time. And notice that I took the previous y value and added it to that change in order to get my new value. So in other words, I took 1.1 and added my change, which was 0.11, to the 1.1. This is the 1.1. This is your change, which was 0.11. I hope that makes sense. You can do it all out in this form. That's what happens sometimes. But I kind of like this little bit of shortcut method as long as you remember that you increment as you go down for the y's. Okay, example number 10. Use Euler's method to approximate the particular solution for the differential equation y prime is equal to x minus y passing through this point, and delta x is equal to 0.2. So notice my x starts at 0. It won't always start at 0, but I can go like this because my delta x is 0.2 every time. My y is going to start off at 0.5. However, I don't know what my change is until I figure out this value right here each time. So let's find out what dy dx is. Remember, dy dx is this x minus y. So it's going to be negative 0.5 because it's going to be my x minus my y right there. Then delta y is going to be equal to my slope, which is negative 0.5, times my delta x. My delta x is 0.2. That's what they tell me. So this would be negative 0.1. So that is my change in y. So what I'm going to do is go over here. I still have my 0.5, but then I'm going to change by negative 0.1. So when I come off of that, I'm going to end up with 0.4. dy dx is x minus y, so I'm going to end up with negative 0.2. And you should probably pause this and try to do these steps yourself, otherwise you're not going to know what to do. Then I do this step, which is the slope, which is negative 0.2, and then I multiply by my increment. So this is going to be negative 0.04. Delta y goes down here, so I'm going to be now at 0.36. Delta y would be, oh, now I'm in positive territory, so this would be 0.04. And then delta y is equal to my slope, which is 0.04 times 0.2. So my change in y is going to be 0.008. And so I add that on here. So that's my estimate at 0.6. So I'm going to be 0.368. Can't possibly graph that appropriately, but I'll try. But that would be an estimate for 0.6. Go ahead and plot those and see what the curve looks like. So this looks like an estimate of my curve. All right? Now, you could go solve this differential equation, but I don't know if we can do this by separation of variables. Probably not. So we maybe can't see what it looks like, but this is an estimate of the curve. Now, unfortunately, I have example 10 and example 11 on two different pages, but they give you the slope field on example 10, and they say, okay, what is my solution look like if I kind of follow the curved lines to the slope field? Will it look like this? So that's what we have to keep in our memory for example number 11. So I'm going to draw this, drop my hat in the water here. If I come down like this. It looks like it flattens off. And then as I get over to the other side, I look like I start going up again. Does that look like what we just did? Yes, very much so. Okay, so that gives you an idea of the combination between the slope field and then also Euler's method. You're kind of doing the tangent lines as we go along to figure out this solution curve, an approximation of it. Okay, so that's Euler's method. Euler's method is approximation for the curve, or you can even figure out, it's kind of like combination of many tangent line approximations as we go along. That's all it is. All right, I hope you enjoyed this, and thanks for listening, and I hope you have a great day.